is Lucy Mo, and today I will be showing you two demos on an image classifier that I built. I'm currently a student studying in Vancouver, BC, and I just completed my grade 10 year. I'm very interested in AI and technology, hence I'm at the MIT Hand Lab for 2 weeks. With the guidance of the lab, I have built this program in Python. Before the demo, I will be giving you a small introduction about neural networks, so if you already know about them, click the timestamp here. Neural networks are computer programs that approach the problem from a different direction. It can be inferred from the name that neural networks are somewhat comparable to human brains. They can both learn. However, a neural network learns by looping over training examples hundreds and thousands of times and performing calculations over and over again. Therefore, neural networks can be very costly, especially if you need a very high-tech device to run it. So researchers today are discovering new methods to increase the efficiency of these programs so that they can be run on edge devices such as a $65 Raspberry Pi, as I will be showing you later. The purpose is to democratize these programs, meaning that everybody can have access to them. The best way to achieve this is to increase the efficiency of the program. Without highly efficient programs, the devices used to run these programs will have to be very, very pricey, and not everybody can afford that. Today, I will be demonstrating for you two demos of a Handmotion classifier. A classifier is a program that can distinguish between two or more classes, in this case, the Handmotions 1 and 5. I built this neural network using Python. This neural network is built with TensorFlow Keras and deployed with TensorFlow Lite. TensorFlow is a Python library or a collection of functions used to build this neural network. There will be two demos in this video, a laptop demo and a Raspberry Pi and webcam demo. In both demos, the camera will be taking an image, the program will process the image, and the terminal will output either the word 1 or 5 based on my hand gestures. The neural network is able to distinguish between these hand motions because it has learned parameters based on the training data I have inputted. The training data consists of 280 distinct images evenly split among the motions 1 and 5. The program first randomly initializes these parameters. Then after each iteration or epoch, it tunes these parameters based on how wrong they are. And the incorrectness of the neural network is denoted as loss. So the neural network calculates the loss, then tries to optimize it using an optimizer. In the end, when the loss is minimal, the neural network has learned the parameters and is able to differentiate between the two hand motions. On to the demo. First, I will launch the program. And this demo is a laptop demo, so the camera will just be the built-in camera. So I will launch the program, and it's running. Okay, to the left of the screen, you will see a live camera input feed. So if I wave to the camera, it will show on the screen. To the right, you have a terminal which is outputting the results of whatever is inputted here. Right now, it is incorrect because there are no hand motions in here. So if I put a 1 in front of the camera, it'll output a 1. And if I switch that to a 5, notice how the terminal outputs a 5. And I can also alternate between these, so 1, 5, 1, 5. So this proves that my neural network is able to distinguish between these two hand motions based on what the camera is taking in. Next, I will be showing you a demo on the Raspberry Pi and webcam. So this right here is a Raspberry Pi 4B, and it is essentially a mini computer, except it has a lot less computational power and is a lot cheaper than a normal computer. It is connected to this webcam right here, a Logitech webcam, which will be serving as a camera for this demo. As you can see here, the Raspberry Pi takes around 5 watts to run the program, while the laptop takes around 45 watts. This shows the difference in energy consumption between the two devices. So on the screen, you can see that I have the terminal open for the Raspberry Pi. However, there is no live input feed, and this is the difference between the two models. And I am accessing the desktop of this Raspberry Pi to display the terminal, and this is done through a VNC viewer. So so now I'm going to launch the program. Notice how it takes longer to launch because of the weaker computational power. So now it's outputting results. So in front of the camera, if I hold up a 1, it will output a 1. And if I hold up a 5, notice how the terminal outputs a 5. So if I alternate between the two, the terminal will also alternate between the two results. So this proves that my program is also able to be run on a Raspberry Pi, which is a lot less powerful computationally. My final model is built with TensorFlow Keras and has a total of 8 blocks. On the screen right here, you can see the computational graph. So there are 5 convolutional blocks and 3 fully connected layers. For each of the convolutional blocks, the number of filters increases by a factor of 2. And the kernel size for the last 4 is 3 by 3, each with an activation rate loop. And for the max pool layers, for the max pool blocks, there are kernels of 2 by 2 and strides of also 2 by 2, which is very standard. So the input data is size M being the number of training examples, 224 by 224 by 3, because there are 3 channels for RGB. So after the end of all these 5 convolutional blocks, the output is flattened into a M by 128 times 3 times 3 matrix. And this fully connected layer then produces an output of 64 and has a dropout rate of 0.5. For both of these fully connected layers, the activation is rate loop. The second one also has an output of 64 and a dropout rate of 0.5. For the final layer, the output number is 2 because there are 2 classes, and there is no dropout and an activation of sigmoid because of binary classification. And we produce an output of M by 2. This model is very simple and is capable of being run on a Raspberry Pi with just under 5 watts, while on a MacBook Pro here, it takes around 45 watts. This difference may not seem like a lot right now, but if you were to deploy this program on a bigger scale, then it will be the crucial factor towards cost and accessibility. As mentioned before, if we want everyone to access AI technology, then the efficiency of the program will be crucial. In the future, increasing the number of classes for the program so that it can recognize motions such as up, down, left, and right would be great. Moreover, if we used a series of images for the data set instead of just one image, the program can recognize motions such as swiping and zooming in and out. Those will be my next steps. This program can then be deployed on applications such as maps, where you could just zoom in and out of the map without having a touchscreen, which can be costly. Also, this can be deployed in a hospital scene where patients can order food on the screen without having to actually access a remote control, or they could open like the window up and down, and they could even adjust the angle of their beds. Again, to make this accessible for everyone, the energy efficiency of the program is very, very important. And it must be computationally cheap enough to be run on devices such as a Raspberry Pi. Thank you for watching, and check out my GitHub page in the description box below. You will also find a link where you can implement your very own Handmotion classifier. Stay tuned for updates and future programs. Bye now!